Welcome to Lecture 55, where we'll be looking at molecules first and then at solids formed of many, many atoms put together. Now, in principle, both of these things are governed by the Schrödinger equation, and you ought to be able to solve the Schrödinger equation to determine the structure of molecules and structure of solids. But you certainly can't do that analytically. That is, you can't do pencil and paper and find functions that describe the wave functions of molecules. Increasingly, you can do it with computer programs. And 20 years ago, if I were teaching this course, I probably would have said, well, we really can't understand molecules in terms of the Schrödinger equation. But now we can, because we do increasingly complex molecules by computer simulation. In fact, you could argue that the entire world is a solution to the Schrödinger equation if only we knew how to solve it. And we're at the point where we can do those solutions for molecules. Here's an example. This is a computer simulation of the structure of a complex molecule, namely aspirin. And what you're seeing here are yellow circles, which represent carbon, red circles, which represent oxygen, and blue circles, which represent hydrogen. And you see the web-like pattern around the whole thing, which represents the cloud of electron probability that surrounds this complicated molecule. So just like we were talking about atoms having electron probability clouds, so do molecules. And this is a computer simulation calculating what the structure of the aspirin molecule ought to be. That's a complicated structure. Well, how would you make a molecule? Let's take a look. So let's start starting with just a simple molecule consisting of two atoms, a so-called diatomic molecule. And we're going to start with the two atoms widely separated. We're going to hold one fixed, and we're going to bring the other one in, and we're going to ask, what's the potential energy of this situation? When we dealt with potential energy curves way back in the mechanics lectures, so we understand potential energy curves. And we're going to start with the zero of potential energy taken when these two things are very far apart. And as I bring them together, they begin to feel slight attractive forces. Why? Because although these atoms may be electrically neutral, they have different distributions of positive and negative charge, and as they come together, those distributions of charge induce dipole moments, remember the electric dipole in each other, and there's a very weak dipole-dipole attractive force, and that causes an attraction. Another source of attraction is quantum mechanical. Because of that pairing of spins in opposite directions, that pairing is energetically preferable. As these atoms come together, there's a slight attractive force associated with opposite spin electrons. So there are two attractive forces, and that causes the potential energy to drop from zero, telling us we're in a bound state where the two atoms have been attracted, where it would take energy to separate them further. So as this process continues, the attractive force decreases the potential energy, and we're plotting the potential energy curve as that atom moves in. So we're plotting it as a function of the atomic separation. And those attractive forces get stronger as the atoms get closer together, so the potential energy goes down and down and down. But when we reach a certain point, we begin to feel repulsive forces as well. What's the origin of the repulsive forces? Two things. One is the ordinary Coulomb repulsion, the electrical repulsion associated with the positive charges of their nuclei as they get close enough together for the nuclei to experience each other's repulsive electrical force. We begin to feel repulsive forces. Another repulsive force is quantum mechanical. We have electrons in these atoms. Originally, the atoms are entirely independent, but as they become close together, the electrons sort of know about each other and their wave functions, and the exclusion principle says they can't be in exactly the same state, so there end up being slightly higher energy states, and that causes a repulsive force. And so eventually we bottom out, and then as the atoms get very close together, the repulsion would grow very greatly. And there is a minimum potential energy, and that minimum potential energy represents the equilibrium separation of a stable molecule. By the way, at that equilibrium, as is almost always the case at the equilibrium in a potential energy curve, the curve is essentially parabolic, and that tells us that small deviations from that equilibrium will result in simple harmonic motion and simple harmonic oscillation. So that happens for molecules as well as for large mechanical systems. So there's how we've made a molecule. Now, that's just sort of symbolic. There are actually several different ways that molecules can bond together. Let's look at some of them. For example, there's something called an ionic bond. In an ionic bond, one atom that is prone to giving up an electron and another atom that's prone to receiving an electron come together, and the one atom, it becomes energetically preferable for the one atom to lose its electron to the other. And now we have two charged particles, and they're bound very tightly together, and they produce things like salt. Sodium chloride here, ordinary table salt, is a very tightly bound crystal. It's tightly bound because of that ionic bonding. That's what gives it, by the way, its very high melting point. there's a very common kind of bond called a covalent bond. A covalent bond is a bond in which atoms share electrons among themselves, and it's the sharing of the electrons that gives rise to a lower energy state that represents the binding together. The electrons pair with opposite spins, and they're in a single molecular orbital state, but because they have opposite spins, they can still obey the exclusion principle. And here's a kind of picture of the electron probability cloud in a simple diatomic molecule like hydrogen H2, oxygen O2, nitrogen N2, the second two molecules making up the bulk of the atmosphere. H2O, water, is also covalently bonded, a very common bond. And another example of a covalent bond is the bond that holds together C60, Buckminster fullerene, the wonderful soccer ball-shaped molecule discovered only a few decades ago and named after the famous Buckminster Fuller. So there's a covalent bond. There are hydrogen bonds which occur as the tiny, tiny nucleus of hydrogen, which is just a single proton, is able to nestle down close to other structures. Hydrogen bonds are fairly weak. They bond ice crystals together. They bond the water molecules to form ice. They also bond the DNA helix into its double helix structure. They don't bond the individual atoms that make up DNA, but they bond the helix with this relatively weak bond. So there's the ice crystal. There's a van der Waals bond, which is, again, that very weak bond associated with the dipole-dipole interaction. It's a very weak bond, but it's another form of molecular bond. So chemists worrying about molecules think about all these different types of bonds. And finally, there's the metallic bond, which is the bond that holds metal atoms together in a large chunk of metal, and it's a bond that's forged by all those free electrons, which you'll remember from the electricity and electric current lectures, are free to roam throughout the metal, and they exert a bonding effect that holds the metal all together, basically an electrical bond. So the free electrons act as a glue. We can't get too quantitative in this lecture, but let's get a little bit quantitative and talk about quantization in molecules. Molecules can rotate, and because they can rotate, they have angular momentum. The angular momentum is I omega, and it turns out to be quantized by that same kind of formula I introduced last time for quantization of angular momentum. There is a quantum number which can be 0, 1, 2, 3, or so on associated with the angular momentum. It's an integer, and the actual angular momentum is the square root of L times L plus 1 multiplying h bar. That's the actual angular momentum in a rotational state. That leads to energy quantization because the rotational energy is the analog of a half mv squared. It's a half I omega squared. And if you work that out using the quantized angular momentum above, you get L plus 1 times h bar over 2 times the rotational inertia of the particular molecule. So energy in molecular rotation ends up being quantized. There's also the possibility of molecular vibration. We saw that the molecule is sitting on average at its lowest point in its potential energy curve, and because that curve is parabolic shaped, it can undergo simple harmonic vibrations about that equilibrium. And we already looked at the simple harmonic oscillator in quantum physics, and we found it had these energy levels given by n plus a half times h times the frequency of the vibration, or n plus a half h bar omega. You can express it either way. The lowest energy state has a half hf of energy, and they go up in steps by hf there. The levels are separated by delta E equals hf. So that tells you that transitions among vibrational energy levels in an atom are going to carry photons, are going to involve photons of energy hf. So the spectrum of a molecule is actually somewhat complicated. And what I've shown here in this diagram at the upper right is the n equals 0 vibrational level of a particular molecule, and above it is the n equals 1 level, and there'd be higher levels up, although you get up very much higher and quickly you lose that parabolic simple harmonic energy, simple harmonic oscillation kind of energy relationship. So here we have the n equals 0 and the n equals 1 vibrational levels, and each of those has many possible rotational states. And if you look back at the rotational energies, they were quantized by L times L plus 1, so there's an L squared in there, and they aren't evenly spaced, so you see them not evenly spaced. And it turns out that transitions between these levels require a delta L, a change in that angular momentum quantum number of plus or minus 1. It can't be 0. And you've got to have delta n of plus or minus 1. So there are a whole host of transitions possible between energy states in rotating and vibrating molecules. And it leads to evenly spaced spectral lines because of that simple harmonic nature of it, and also the way these different levels, these different transitions go from different levels according to those rules, delta L equals plus minus 1 and delta n equals plus minus 1. Turns out that molecules are a little heavier than atoms, So their vibrational frequencies are therefore a little bit lower, and their rotational frequencies and so on. And so they turn out to involve mostly infrared photons. So molecular spectra tend to be in the infrared region of the spectrum. And here's an example. This is an infrared absorption spectrum of chlorine. This was taken by a colleague of mine at Middlebury College using an infrared spectrophotometer, device that measures the absorption of infrared. And the wavelength in now micrometers rather than nanometers at the bottom, we're at wavelengths that are, about 5, 6, 7, 8 times that of visible light. So these are much longer wavelengths, lower frequencies, infrared. And you see spikes. On the left, you see a series of spikes. Those spikes correspond to the transitions that are shown in the left-hand part of the diagram at the top. And then you see another series of spikes at the right, and they correspond to transitions which are shown in the right-hand half of the energy level diagram at the right. There's a couple other interesting features of this diagram. One is you see that most of the spikes are actually double, and that's a result of the fact that chlorine, unlike most common substances, has 2 isotopes, which we'll talk about in our nuclear lecture shortly. 2 isotopes with different masses. They're still both chlorine. They have the same number of protons, but they have different numbers of neutrons in their nucleus, and you're seeing the slightly different masses that result in slightly different rotational inertias and therefore slightly different energies. I should say one other thing about this rather abstract-looking diagram. This is the reason for one of the biggest environmental problems of our time, namely global warming. Not with chlorine, but with the molecular, vibrational, and rotational spectra, particularly of slightly more complicated molecules, H2O and CO2 particularly, the infrared absorption by those molecules undergoing transitions among different rotational and vibrational states is what leads to the absorption of outgoing infrared radiation, the trapping of heat in Earth's atmosphere, and to global warming. And as we put more of those gases, particularly CO2, in the atmosphere, that effect increases. And one thing you'll notice in this spectrum of chlorine is that there are lots of closely spaced spectral lines, lots of closely spaced energies. There's almost a band of energies. And CO2 and O2 and H2O and other gases in the atmosphere, but particularly CO2 and H2O, have these bands of almost continuous wavelengths where they strongly absorb infrared radiation. And that's the ultimate cause of global warming and the greenhouse effect and so on. So there's as much as we can do in terms of quantization in molecules. We've been able to quantize the vibrational energies and the rotational energies, but we can't go much further with that. Let's go on to solids, a really hot topic in contemporary physics and microelectronics. Used to be called solid-state physics. We tend to call it more condensed matter physics to reflect a wider array of kinds of matter that are in this condensed state where atoms are close together. And condensed matter physics is usually described in solid-state physics by what's called band structure. And I want to show you here where band structure arises, and then I want to give you some practical applications of this, particularly in contemporary electronics. So let's consider what happens when we bring atoms together. We start with 2 atoms, and they're initially completely separated. So in this diagram, the horizontal axis is molecular separation. And way off at the right, you see these 2 different states of the atoms. We see the 1s state and the 2s state, states that we talked about last time in describing atoms. But as the atoms come closer and closer together, their electrons begin to overlap. And then they begin to have to worry, if I can anthropomorphize them a little bit, they have to worry about that exclusion principle that says 2 electrons can't be in the same state. Now, when the atoms were way far apart, 2 electrons could be in the 1s state, and they're completely independent atoms, that's okay. But as the atoms come together and those electrons sort of sense each other and begin to be shared, they can't both be in exactly the same state. And so the energy level has to split, and there have to become 2 different energy levels. As we move these atoms closer together, you see this splitting of the energy level, and you see that dip that represents a kind of equilibrium configuration. Both these energy levels have split when we bring 2 atoms together. What happens if we bring more atoms together? If we bring 5 atoms together, what has to happen is each of those energy levels splits into 5. Now, solids, as opposed to molecules, are not made of a few atoms. They're made of zillions of atoms. A typical macroscopic-sized object, like a grain of salt or a brick or something like that, has somewhere on the order of 10 to the 23 or a few more orders of magnitude number of atoms in it. So when we bring that many atoms close together, we get many levels of these splitting, and we get basically a band of available energy states that are available to the electrons in that solid. It shows just a continuous band shaded in gray. And I've marked the equilibrium separation, which marks the point of lowest energy in that lower state, in the upper state, and that is where this particular solid will want to sit, with that particular interatomic spacing, and then these bands of energies available. And you'll notice between those two bands, there's what's called an energy gap. No electron is allowed to have an energy in that gap, for the same reason that no electron was allowed to have an energy between the allowed orbits in the Bohr model, or better, the allowed orbits that are allowed by the solutions to the Schrödinger equation for that particular atom. That's the origin of this band structure that we talk about in solids. Now, this band structure is going to explain for us a great deal of the difference between different kinds of materials, in particular their different electrical properties. Let's take a look at that. Here's the band structure of a many-atom solid at its equilibrium separation. And I'm just showing the bands associated with the outermost electrons in that solid. There may be lots of other electrons further in. Their bands are really not very interesting to us because nothing much happens. They are full of electrons and nothing interesting happens. But in this case, I've drawn a 1s band and a 2s band, but there really could be higher and there could be lower bands further down. And the energy is going up on the left, and I'm not drawing any shape to this. The horizontal axis doesn't mean anything because I'm drawing a picture at the equilibrium separation for that solid, the bottom of the curve in the previous band level diagram. So there's what the band structure of a solid looks like. And there's this energy gap. No electron states, no allowed energies in that gap. If a material is an electrical insulator, it's a material in which the states in that lower of these two outermost bands are completely occupied by electrons, and the other state is completely unoccupied. Sometimes we call the lower one the valence band and the upper one, because it's the valence electrons that participate in bonding with other atoms, and the upper one is called the conduction band. In this case, there's no conduction occurring because we've got an insulator. And the reason we've got an insulator is because if you apply a little bit of energy to one of the electrons in that lower band, near the top of that lower band, all the energy levels are occupied. There's no nearby energy level to promote it into. To get it to where it's free to move around, where it has other energies available to it, you've got to bump it all the way up into that higher state. You've got to cross that energy gap. And under typical conditions of electric fields applied by batteries and generators, or a lot of thermal activity, or even photons coming in or something, there isn't enough energy to do that because the energy gap is too big. So that's an electrical insulator. An electrical conductor, on the other hand, is a material in which the outermost band that has electrons in it normally is only partially full. For example, an alkali metal like sodium has only one electron in its outermost shell. It could have two, and that means when you put a bunch of sodium atoms together to make metallic sodium, you end up with only half that band being full. And what that means is, if I apply a slight electric field to this material, or give one of those electrons in that uppermost band just a tiny bit more energy, there are plenty of unoccupied energy states, allowed energy states available to it, and with a very little bit of energy, a very weak electric field, I can promote it into a higher energy state where it's free to move about. And consequently, this material is an electrical conductor. And that's a rather more sophisticated look than we did back in the electricity chapters. It's a quantum mechanical look at the difference between electrical insulators and electrical conductors. Electrical insulators have completely occupied bands and then an energy gap before there are any unoccupied states, and it takes a large amount of energy to promote electrons into the unoccupied states and make it conduct. You could do it, but by the time you did it, you'd probably have enough energy to destroy the material or wreak havoc on it in other ways. Whereas in a conductor, it takes very little energy to promote an electron to a new unoccupied state. And so you get conductivity very easily in conductors. Now, the interesting thing, and here's where the rest of this lecture is going to get into something more practical than most of the recent lectures have been, is if we look at materials called semiconductors. And materials called semiconductors are materials in which they're actually insulators. They're perfect insulators at absolute zero. And so here I have a picture of a semiconductor at absolute zero, and it looks just like my picture of the insulator. It's got a fully occupied lower band, a fully unoccupied upper band, and it's got this energy gap. It's not like a conductor. However, if I go to a temperature greater than absolute zero, that gap is so small that random thermal vibrations can promote occasional electrons into the conduction band. So the only real difference between an insulator and a semiconductor is the semiconductor has a much, much smaller band gap. And thermal energy at, say, normal temperatures like room temperature promotes electrons into the conduction band, and we get some conduction. Semiconductors are not great conductors just intrinsically by themselves, but they're okay. They do conduct electricity. More importantly, semiconductors are at the heart of modern electronics because we can manipulate their electrical properties by manipulating their band structure. And I want to show you how we do that, and then I want to show you a couple of devices that work on that principle. We dope semiconductors. We add very small quantities of impurities, typically at the level of about 1 part in 10 million or so. Very small amounts of impurities. And here's what they do. They, first of all, make the material become a good conductor. And we can do that in 2 different ways. So we make them good conductors in 2 different ways. If we add extra electrons, we have what's called an N-type semiconductor. So here's an example. I've got a crystal of silicon. Each silicon atom bonds to 4 other silicon atoms. It really happens in 3 dimensions, but I've reduced it to 2 dimensions here to show it to you. And so there are these bonding electrons taking part in that bond. If I introduce a phosphorus atom, it has 5 valence, 5 bonding electrons. And if I put it into this crystal structure, it'll fit uncomfortably in there, but 1 electron will go wandering free through the material. And therefore, I'll have suddenly a lot more free electrons, even if I put a small level of this dopant. And this material becomes a good conductor, and it conducts by the movement of free electrons. By the way, there's a very common misunderstanding about that N designation. People think, oh, it's negative. It's not negative. The phosphorus atom is neutral. What it does have is free electrons, free negative charge carriers. The things that can carry current are negative. But to say a material is N-type is not to say it's negatively charged. In fact, as we'll see, it's sometimes positively charged. So the conduction in this N-type material is by electrons. If we look at the band structure of this, we get these new levels. They're called donor levels, and they're near the conduction band. And since they're very near the conduction band, it's very easy for small amounts of energy to promote these electrons into the conduction band and cause a lot more free electrons to be there, and so a lot more conduction. So there's the band structure diagram for an N-type semiconductor. Now we can do something else. We can add a material, like in this case boron, that only has 3 conduction electrons and 3 valence electrons, and that's too few. It still nudges into the semiconductor structure, into the crystal structure, but we're missing one of those electrons that forms a bond, and instead there's a hole, a place where an electron is missing. And this is a funny idea, but a nearby electron that's still bound in that structure can fall into that hole, and then the hole has effectively moved. And the hole, although it's nothing but the absence of an electron in the crystal structure, can nevertheless move through the crystal structure and cause conduction. And so we have conduction by holes and electrons. 2 types of semiconductor material, and the band structure shows that we have these so-called acceptor levels down near the valence band, and it becomes easy to promote charge carriers into those bands. So we have 2 kinds of semiconductors. And one of the biggest and most important things in contemporary physics, at the heart of most electronic devices, is to put a piece of P and N-type material together. If you do that, there's a lot of free electrons in the N-type, and so they diffuse across that junction and end up, some of them, in the P-type, actually making it negatively charged. There's a lot of holes, positive charges, in the P-type, and they diffuse across the junction into the N-type. And the result is we have positive on the right, negative on the left, and as a result, there is a zone where there are very few free charges because the positive holes combine with the negative electrons, the negative electrons combine with the positive holes on the left, and we have a region where there are very few free charges, and so we don't conduct electricity very easily. We also have a big electric field pointing from plus to minus. That's what a p-n junction looks like. And there's a band diagram for a p-n junction. Associated with that electric field is a rise in the potential energy of electrons. Remember, electrons are negative. They like to go against the electric field, so for them to go with the electric field requires that they gain energy. You give them more energy. So that's what the band structure looks like. If we put a battery across that junction with its positive connected to the N-type, we only make that electric field bigger, and we make it even harder for electrons to get through, and so that device does not conduct electricity in that direction. But on the other hand, if we reverse the battery and put the positive to the P-type, we reduce that electric field, we reduce that rise in the band structure, and therefore we make it relatively easy for current to flow through that device, and the p-n junction turns on. So the p-n junction acts like a switch. It conducts electricity in one direction but not the other, or like a one-way valve. It's on in one direction but not in the other direction. And that whole idea, that whole concept, is at the heart of almost all modern electronic devices, including the transistors, which are the ubiquitous devices that do the on-off switching in our computers, that help store information in our computer memories, that amplify audio signals in our stereo systems, and so on. And I want to look just briefly at two devices that use that p-n junction. Here's one example. Here's a photovoltaic cell. A photovoltaic cell is a p-n junction with a very thin n-type layer at the top, so thin that it's basically transparent and light can get through it. And what happens is light comes in the form of photons. The photons can give up their energy, if the photon energy is roughly comparable to the band gap, give up their energy and form an electron-hole pair, and that electron-hole pair ultimately drives a current of electrons through an external load, and that's how you make electricity with no moving parts from nothing but sunlight, which, by the way, provides 99.98% of all the energy coming to planet Earth. A great way to make electricity, if only it were a little bit more economical. So there's a p-n junction. The opposite of a p-n junction being used for a photovoltaic cell is a p-n junction which, again, has a band gap carefully engineered to give off photons in roughly the visible region, or maybe the infrared, or maybe some other region of the spectrum, but mostly infrared or visible. And when you forward bias that diode, that is, you connect a positive terminal of the battery to the p-type material, you drive a current through it, and as electron hole pairs recombine, they give off photons with energy equal to the band gap energy, and out comes visible light. And if you design the thing carefully with mirrors on the end, you don't just get light, you get a laser. So all the things you have with LEDs, and in a few years that will be every light source as we phase out incandescent lights because they're so inefficient, and then get rid of those slightly awkward compact fluorescents, they will be LED sources, light-emitting diodes, and this is how a light-emitting diode works. Well, let me wrap up with two other examples of solid matter, which I want to get into just briefly, just mention them. One is superconductors. In superconductors, these are materials that below a certain temperature, I've mentioned them before, they conduct electricity with absolutely no resistance. And the way that works is, in the superconductor, two widely separated electrons, they may be a million electrons in between them, but nevertheless, they're quantum mechanically paired in that they essentially share a common wave function, and that pairing is mediated by the effect the electrons have on slight disturbances of the crystal lattice. It's a rather complicated mechanism, but that kind of solid has zero electrical resistance. That's a superconductor. Another remarkable kind of solid is what's called degenerate matter. Degenerate matter is great big bulks of matter that are so tightly crammed together that basically all their particles are sort of acting as one. And so just as we got those bands in the solids, now we get energy levels completely full to the lowest level, higher and higher and higher, and more electrons. They have to go into higher and higher energy levels. They can't all be in the ground state. And an example of this degenerate matter, several examples, are the matter that makes up neutron stars, balls of neutrons with as much mass as the sun crammed into a few miles, and white dwarf stars in which the atoms are completely collapsed on themselves, and so they're basically all in one state. And so this form of degenerate matter has very high energies associated with its electrons, not because they're hot or something, but because they simply can't lose any more energy because they can't drop down any lower. So those are two examples of unusual quantum solids. Well, let's wrap up. We've looked at molecular binding mechanisms, ionic, covalent, hydrogen bonds, van der Waals, etc. We've looked at molecular quantization of angular momentum and of energy, rotational and vibrational both. We've looked at solids. We've studied how atomic energy levels become bands. We've seen insulators, conductors, and semiconductors. We've looked at doping. We've looked at some applications of semiconductors using this idea of the p-n junction. And finally, we took a brief look at degenerate matter and superconductors. Well, let me end with a practical engineering challenge. The challenge is about Blu-ray. If you've got a Blu-ray player or you've worked with Blu-ray discs, they're fairly recent inventions. And the reason they're fairly recent inventions is that technology was enabled by the development of a laser, p-n junction laser, emitting blue light at 405 nanometers wavelength. That's very near the blue end of the visible spectrum, which ends at about 350 nanometers. It is not easy to make very short wavelength p-n junction lasers. You need a big band gap because there's a big photon energy associated with them. So this device had to be engineered, and it took a while in the history of electronics to do that, and that's why Blu-ray is a fairly recent invention. It's Blu-ray because this laser is emitting blue light as opposed to the redder light that's used to read conventional DVDs and even redder light that's used to read CDs. So the question is, what's the energy gap of this semiconductor? If you were the semiconductor engineer, what energy gap would you have to give it? Well, let's look at a solution for this problem. We know that the energy gap, this delta E, is HF, where F is the frequency of the light associated with the photons we want to emit that have energy delta E. F is C over lambda. We're told lambda is 405 nanometers, so we'll do the calculation. H times the speed of light over 405 billionths of a meter, 10 to the minus 9 meters. Answer is 4.9 times 10 to the minus 19 joules, or about 3 electron volts. So it was the engineering of a 3 electron volt gap semiconductor material that enables Blu-ray technology.